So we're gonna take the two molecules up top, and we're gonna distill them down into this one, just for the first question to answer: how do we predict the product of these reactions, right? And that's not to say we can ignore this isopropyl group. It's just to say we'll get to it. We'll get to it at a later point, right? To talk about it. Okay, so when we look at this reaction, consider our starting material, consider our reagents and conditions. What type of reaction is this likely going to be?
Elimination.
Elimination, good. And which you know which elimination? E1 or E2?
E1. E2.
E2, good, yeah. So we have a strong base in here, right? And that indicates that it's going to be an E2 elimination. Right, so that informs us of the mechanism that we can use in order to do that E2 elimination. You can see we have our leaving group in the tosyl group, right? And really there's only one proton that can be pulled with the relationship that allows us to do elimination. Right, so we're just going to draw out a mechanism here, right, showing us pulling that proton, forming the pi bond, and kicking out the tosyl group. And that's what the products, both products, are going to look like, right? Formation of the double bond between the methyl group and where that tosyl group was. Right, now, in order for this to happen, whenever you do an E2 reaction, there has to be a special relationship spatial relationship between the leaving group and the proton that's being pulled. So what relationship do those two have to have? Yeah.
Anti-planar.
Yeah, an anti-periplanar relationship, right? So it's going to actually help to draw this out as a three-dimensional structure to understand if this elimination can, in fact, take place. Right, so let's take our starting material and draw it as a chair. Right, so here's the center with the tosyl group on it. You can see the tosyl group is a wedge, right? So it's coming up toward you. So it would be on top of the ring in the chair structure, right? The methyl group is also a wedge coming out towards you, so that should also be on the top of the ring in the chair structure. You can see while the tosyl group is axial, right? The methyl group is equatorial. Right? And then the other carbon has two methyl groups, so hopefully everybody can understand why elimination would not take place down that other bond. Right? If we look at the tosyl group, we can see that there's an anti-periplanar hydrogen on the carbon next door. Right? And this is really important in six-membered rings, that in order for elimination to take place, the leaving group has to be in the axial orientation. Right? It cannot be equatorial, because if it's equatorial, the only bonds that are going to be anti-periplanar to it are going to be the bonds of the ring. Right? There aren't going to be any protons that have an anti-periplanar relationship with an equatorial group. Right, so what this means is when this chair adopts the opposite conformation, whenever it undergoes a chair flip, that tosyl group is not going to be axial, right? It'll be equatorial, and elimination cannot take place whenever the molecule is in that conformation. Right? So it has to be able to adopt a conformation where it has an axial leaving group. Right, questions about that? Right, so why does this orientation, or why does this relationship have to exist for elimination to take place? Let's review that.
280 degrees.
Sorry,
280
degrees?
Good, yeah, so they have to have a 180-degree relationship, and why is that? Like, why does that specific dihedral?
There's something to do with hyperconjugation of the H.
It's not hyperconjugation. No. I guess we can kind of think of it as hyperconjugation, but usually hyperconjugation is stability, and that doesn't lead to a reaction. Yeah.
The electrons in the hydrogen bond need to overlap with the antibonding orbital of the sulfur group.
All right, so we have our antibonding orbital, sigma antibonding orbital there, right? And those that sigma antibonding orbital has to overlap with the carbon-hydrogen sigma bonding orbital. Right? The only way for that to happen is if they are in an anti-periplanar 180-degree dihedral relationship. Right? And that way, the sigma electrons, which become the pi electrons, right, can overlap with the antibonding orbital, kick out the leaving group, right, and form the pi bond. Questions about that?
Could you just repeat that last part again?
Sure, yeah. Yeah, so in order for elimination to take place, so I'm going to just draw this out as a sawhorse projection. Have all the other groups as R groups. So in order for elimination to take place, the bonding orbital of the proton that's being pulled, sigma bonding orbital, has to have an or has to align with the antibonding orbital of the leaving group. Right, so this is the sigma star of the leaving group. This is the bonding orbital of the hydrogen that's being pulled, and in this case, these two orbitals are aligned. Right? The only way to accomplish this is if the leaving group and the hydrogen that's being pulled have an anti-periplanar relationship, right, or 180 degrees from one another. Right? Because that's the only way for those orbitals to line up. Yeah. Any other questions? I mean, this is a pretty important aspect of E2 elimination, so if you do have questions, let me know. Okay, so the question now becomes, we know how elimination is going to take place, right? We know elimination can take place down this bond, cannot take place down that bond, right? So we have to ask ourselves what the influence of that isotopic group is going to be, right? So we have to think about these molecules again in 3 dimensions. So the bottom chair here is going to look just like the top chair, except one position is going to be different. Right, so in both of these, right, this is the conformation that the molecules must adopt in order for elimination to occur. Does anybody see a problem with that? Right, yeah.
The isopropyl group is more stable than the top one, so the bottom one is less likely to be in that compound.
Good, right? So when we analyze these two conformations, hopefully you can rationalize that this would be the low energy chair, or the low energy conformer of this molecule. Down here, the biggest group on that ring is the isopropyl group, and it is in the axial position. Right, so there's going to be a lot of 1,3 diaxial strain caused by that axial isopropyl group, right? It's going to be interacting with this hydrogen and also the other methyl group. Right, so as a result, this chair most of the time is going to prefer to be in the flipped conformation. Whenever this chair is in the flipped conformation, tosyl group is equatorial, right? And so elimination is not going to be able to take place, right? Because if we look at the other bonds that would be anti-periplanar to that tosyl group, right? We have this bond here, which is in the ring, and then this bond there, which is also in the ring, right? So there are no protons that have an anti-periplanar relationship with that group in this molecule. So which of these, so to answer the question, right, which elimination is going to take place at a faster rate?
The top one,
Yeah, why?
because you won't have the 1,3 diaxial strain caused by the isopropyl group.
Okay, why is that important?
Because then, like, the hydrogen would be more readily available for, to like stabilize, not stabilize, to donate its electrons.
Okay, yeah, so the hydrogen is going to be more available in order to donate its electrons to form the pi bond. But if you think about this, right, this molecule, say 90% of the time, is going to be in this conformation, or 95% of the time, right? This molecule is only going to be in the conformation where it can undergo elimination maybe 5% of the time, right? And during that 5%, right, it can undergo elimination at the same rate as this, but it has to get into that conformation. And because it's in that conformation very rarely, right, that's going to really slow down the elimination. It's going to basically decrease the number of molecules in the system that can undergo elimination. So that's going to really affect the reaction. Okay, that's not to say you won't achieve it, right? As long as you're heating it enough, waiting long enough for this reaction to take place, you can get that elimination to occur. But maybe for the top reaction, elimination will happen in 2 hours, right? The reaction will be done in 2 hours. And the reaction on the bottom, right, you need to wait 36 to get that to complete elimination. Questions about this? All right, so that pretty much takes us to the end of the elimination chapter. We're gonna move into chapter 14. Chapter 14 deals with alcohols, ethers, thiols, and amines. So some of what we're gonna be looking at in this chapter is a review, right? Seeing how we could form these different functional groups. Some of it's gonna be new, or some of it's gonna be just a little more in depth than we've seen before. We're going to start off on a similar note to where we've been by looking at elimination and substitution of alcohols, and see some of the other things that can occur whenever you use them as starting materials. Okay, so what we're going to be doing is really looking at the hydroxy group as a leaving group, right? And what we need to understand is that, right off the bat, is that OH is a bad leaving group. Right, there we're going to look at one or two reactions this year where OH can be a leaving group. Usually those reactions occur under very strongly basic conditions, really, really harsh conditions. Otherwise, in order to get OH to be a leaving group, you need to do something to it. You need to activate it, right? So one of the ways that we activated OH as a leaving group was by turning it into water. Right, so if we take this alcohol, this tertiary alcohol, treat it with a strong acid, hydrogen iodide, the oxygen is going to pick up the proton. Right, we form our water leaving group. That's going to leaving behind the carbocation. And then the iodide is going to be able to come in to that carbocation center. Right, so the second point, right, OH is a bad leaving group. Water is a really great leaving group, but you often see it employed in unimolecular reactions, right? So unimolecular substitution, unimolecular elimination, where there's a formal carbocation being generated as an intermediate. Right? Problem with this is that carbocations are messy, right? So we typically don't use water, or only under very specific conditions would we use water as a leaving group, right? Take an alcohol, use acidic conditions to protonate and form a water leaving group. And one of the reasons why is because of a reaction that looks like this. so you can see the product that's being formed is probably not the product that you would predict for this reaction. All right, first of all, we're starting with a secondary alcohol. All right, so we know that this is not ideal for SN1 chemistry. Right, and then you can see what we're making is a tertiary bromide. Right, just based on the name, hopefully you can see that the bromine is not necessarily adding to the same carbon that's losing the water leaving group. Right, so let's take a look at the mechanism to try to understand what's going on. Right, so we have our alcohol that's going to interact with the acid, gain a proton. Form our water leaving group, the water will leave. And in doing so, we're forming a secondary carbocation. Now, what we're used to seeing is the bromide, right, or whatever nucleophile we have in here, come in and add to that carbocation center. But there's something that can happen faster, right? Something that can happen internally before that bromide meets up with the carbocation. So remember, right? In order for the bromine carbon bond to be made, the bromide and the carbocation have to float by each other and find one another. Right? It's just not magic or automatic that they do that, right? They actually have to be near each other and interact in the right way, right? So that takes time. Depends on the concentration of the reaction, right? Depends on the heat of the reaction. So before that can occur, this molecule can undergo a rearrangement to make itself more stable, right? And so what we're going to do is we're going to show one of the methyl groups basically leaning over and making a new bond to that carbocation. Right, and that results in the formation of a tertiary, much more stable tertiary carbocation. This rearrangement is called a specific rearrangement. It's called a 1,2 alkyl shift or 1,2 methyl shift. Right? And literally this methyl group here becomes the methyl group on the carbon, one of the methyl groups on the carbon next door. Right? And it's that relief of energy, or relief of strain, right? The increasing the stability of the carbocation that forms that allows this to persist longer, right? And then once that tertiary carbocation is formed, the bromide can come in, and that's going to then lead to the product. right? So hydroxy is a bad leaving group. Water is a great leaving group, right? But it's usually seen whenever carbocations are formed, right? Or it usually leads to the formation of carbocations, which can result in rearrangement. Not always, right? But if they form a carbocation and there's a more stable carbocation that can be formed, then that rearrangement will take place. Sulfonates, in contrast, are also great leaving groups, and they'll typically allow you to do these reactions, elimination, substitution reactions in a bimolecular sense and include elimination, or include rearrangement, not elimination. Right, so if we take that same substrate, turn it into a tosylate. We'll go over this reaction in just a second. Right, and then if we take this tosylate, the sulfonate ester, and if we want to make the bromide, we can treat this with, say, sodium bromide and acetone. Form that bromide. Right, so let's take a look at how these sulfonate esters are formed really easily. Right, so we have our sulfonyl chloride. We have our base. Right, so hydrodimine base, triethylamine is pretty common. Pyridine, not necessarily a hydrodimine base, right, but a pretty common amine base that you can use for these things. Right, so tosyl chloride, or all of the sulfonyl halides kind of have the same general structure. Right, so that's the structure of tosyl chloride, right? So you can see this looks like PTSA, right? With the hydroxy group of PTSA replaced by a chlorine. Right, so seeing what we have here, see if you could really quickly come up with a mechanism to show the formation of the tosylate ester, right? First product we have in this synthesis. one, George? How many people need more time? It was pretty good? Okay. So, the way this works, so I've seen people do this different ways. The most common way that you see is the oxygen adding to the sulfur, kicking out the leaving group first, and forming the protonated intermediate. Then the triethylamine will deprotonate in the second step. Product. Right, so really, really easy to make. The other mechanism that you'll sometimes see is the amine base deprotonating the alcohol, right, and then the alkoxide doing the substitution. That's possible as well. It's just that the equilibrium between the triethylamine, the acid-base equilibrium between the triethylamine and the alcohol doesn't really favor that first step, right? So that will probably be a mechanism in the reaction, but I wouldn't think it's the primary mechanism in the reaction. All right, so these are really some of the options that we have for turning oxygens into good leaving groups, right? We have to activate them in some way, either by protonating them, right, into water, right, or usually in a more controllable way, turning them into sulfonate esters, and then having a sulfonate as a leaving group. Questions about this? No? Okay. So one last reaction. All right, so last semester we learned this reaction where we take carboxylic acids and turn them into acid chlorides. Does anybody remember the reagents needed for this? Okay.
Do you need a wine rub from me?
Not a wine rub. No.
I guess you use vials.
So the reagent that we used here is called thionyl chloride, SOCl2. Like that. So the same reaction can be done with alcohols. Usually have some base in there, some pyridine. Right, and then the byproducts of this reaction are going to be sulfur dioxide and HCl, right? And the HCl will react with the pyridine, which is going to neutralize the reaction. All right, so we're about at the end. So what I want you to do, just for practice before Wednesday, go home, see if you could figure out the mechanism of this reaction. It should be pretty easy, not too far from the mechanism you learned for acid chloride synthesis. So you can take a look at that if you need to. And then we'll pick up in chapter 14, looking at some other alcohol chemistry when we get back.